Thank you for joining this session. And this session begins with a pre-recorded presentation. And after it finishes, there will be a Q&A time, maybe about 5 minutes or less. Okay. I think I can start now, so let's get started. Hello, my name is Byungwoo Lee, and I am a software engineer at Igalia. I've been investigating and prototyping the health pseudo class since the beginning of this year. In this time, I'll briefly share the prototyping progress and introduce the next step of supporting style invalidation with health at the level of abstraction. Adding health is not easy work for me because it is related to the complex and sensitive steps of resolving styles, and it breaks the direction of selector matching and style invalidation, which is important to performance. And there are too many variations that cause different kind of problems. It is easy to get lost in the huge and complex problem. So I'm trying to break the problem down into the smaller problems to get a clear understanding. I hope that this talk can provide a brief summary of that. So what can we do with has? Has pseudo class is one of the logical combinations of the CSS selectors. There can be many expressions that describe the CSS selectors. And while investigating and prototyping has, it was helpful for me to understand the CSS selectors as subject conditions and subtree conditions. We use a selector to select an element in a DOM tree. A selector expression contains conditions of the subject element, but there can be some cases that the condition of the subject element is not sufficient to specify the exact element we want to use. We can specify the exact element by adding conditions of the subtree containing the subject element. We can make more sophisticated condition by adding the subtree conditions. And we can say this a bit differently. If we use the subtree conditions to specify particular subject element, this means that there may be some subtree that matches the subtree condition, and we use the subject element in the subtree. In the CSS selector expression, the subject conditions are always at the rightmost, so the subject element is always the terminal element. But there are other elements in the same subtree, and we have no way to use these elements with CSS combinators. And we can change the subject element with has to use those elements. It is simple. What we need to do is add a has to the condition of the subject element and move the downward subtree condition to its argument. Then the has will be the downward subtree condition of the subject element. Okay, this is the prototyping progress so far. If there is a subtree that matches a subtree condition, we can use terminal elements of the subtree. So we can select and style the elements at terminal, but we can't do that for the other element of the subtree in the usual way. We can use has to change the subject element of the subtree condition. So we can select and style the changed subject element. And we can select elements from other subtrees containing the changed subject element. So we can use other descendant element of the changed subject, and we can use next sibling of the changed subject. We can use descendant of the next sibling of the changed subject, and we can use even more complex relationships. So currently, in the context of static document, you can try almost all expressions using has, except some cases involving tree boundary crossing. So you can try most expressions using has with JavaScript APIs like query selector all matches and closest when you enable the experimental feature flag in Chrome Dev. Also, when you enable has by passing the command line feature flag CSS pseudo has, you can see that most of the has expressions in stylers are working at page loading time or styler changing time. If we have a mutation on an element and the mutation can change the subtree condition, then the subject element style should be recalculated. Style invalidation is a step of triggering style recalculation for a mutation. And has style invalidation is not supported yet. So if we have a style rule using has, the style is not liably changed by a mutation, even if the mutation is can change the has matching state. So the next step is supporting has style invalidation to change the styles lively. Then how to support has style invalidation? Before looking into this, it would be better to focus on the basics of style invalidation, which has to minimize variations as much as possible. So let's check the has invalidation with this simple styler. Class A has class B. First, we need to see how the has pseudo class is involved in the style recalculation and style invalidation process. The DOM is a hierarchical representation of a HTML document, and rendering elements in the DOM requires style properties of each element, such as what is the background color of the element or what is the left margin of the element. And to get the style properties of all elements, we need to take all the stylers and work the DOM tree in pre-order and use the stylers to generate the computed style for each element. To figure out which stylers applies to an element, we need to match each element with the selector of each styler. And some of the computed style are inherited by the children during the style calculation. In this case, we will check the has state only if an element has a class value A. But at this stage, we cannot determine whether the element matches has or not, because we need to know whether the subtree matches the subtree condition or not. So to get the has state of this element, we need to match has argument selector for all the descendants of the element. In this way, style recalculation process resolves the styles of all elements. The has state of an element is true if it has descendant element matching the has argument selector. So in this case, this element matches a selector of this styler. So the style properties in this styler are applied to the computed style of this element. And like previous, some of the computed style of the element are inherited by its children. So to get the has state, we need to match all the subtree element with the argument selector. So matching has is an ON operation where n is the number of subtree elements. And because of this, Matching has is a heavier operation than matching other selectors. In the worst case, if we have a style rule using has, a style recalculation can be an O and square operation because there can be repeated argument matching operations on the same elements. The repetitive argument matching was removed by applying a has matching result cache within a single life cycle, such as a single style recalculation process or a single JavaScript API call. But the ON matching overhead is unavoidable. After supporting the has style invalidation, we may consider an approach of removing the matching overhead by reusing the previous matching result if the has state has not changed. And this is about the style invalidation with has. A mutation can change a has state, and the changed has state can affect style of other elements. In this case, the has state is false for all the elements, but this mutation of adding the class value b to this element changes the has state of its ancestors. And we need to invalidate the style of the ancestor element with class value a to indicate that it needs style recalculation in the next life cycle. So in short, when we have a style rule using has, for a mutation on an element, we need workup ancestors and invalidate the styles. Then the style of the invalidated ancestors will be recalculated in the next life cycle. So is it okay to do this for every mutations? And is it okay for every changed element? And is it okay for every ancestors of the changed element? No, we shouldn't do that because the invalidation and the recalculation are critical to performance. We need to reduce the irrelevant invalidation to reduce the irrelevant recalculation. The style recalculation is basically heavy operation because it tries to match an element with all style rules, and has matching in the recalculation process is even more heavier than other matching operations. So we can try some approaches to reduce the irrelevant recalculations. Some of the ancestor element of the changed element should be invalidated, but many of them don't need to be invalidated. And most elements do not have any ancestors that should be invalidated by any mutation. So how can we differentiate these elements? We can get a hint about this in the has matching step of the style recalculation process. If there was an attempt to match this element with this has pseudo class, it means that the element is affected by the has state change. And if there is an element affected by a has state change, it means that all the descendants of the element are affecting the has state. And the other elements are not related to the has state. So we can mark this information during the style recalculation process. As briefly shared before, during the style recalculation, we work the DOM tree and match selector in style rules and compute the styles. And the computed style is inherited by its children. So when trying to match an element with a has pseudo class, we can mark a flag in the computed style of the element to indicate that it is affected by a has state change. And to mark its descendant elements, we can also mark another flag which can be inherited by its children. The flag indicates that it is affecting a has state. When we walk to the child of the element, the affecting has flag will be inherited. So we can get information about has invalidation from the computed style of each element after the recalculation is finished. Then we can skip invalidation of irrelevant ancestors if the ancestor is not affected by has. And we can skip workup from the irrelevant element if the element is not affecting has. So with this approach, we can add these two filtering conditions for the changed element and for the ancestor element. After applying the approach, we can think about the invalidation for an irrelevant mutation. In this case, the mutation of class value C on the element doesn't change any hash state, but we invalidate the ancestor affected by hash because there is no detail about relevant mutation in the flags. We can get the details about the relevant mutation in the argument of the hash pseudo class. Similar to the existing invalidation set approach in Blink, we can extract features to check the relevance of the mutation from the hash argument. Then, if there is any mutation on an element affecting hash state, we will check whether the mutation matches any of the extracted features. If it doesn't match, we will skip workup ancestors because the mutation is not related to the hash state change. And if it matches, we will workup ancestors and invalidate ancestors affected by hash. With this approach, we can add this filtering condition for mutations. After we apply those, we can think about this case also. If we have multiple style rules using hash, we can invalidate an ancestor which is irrelevant to a mutation, even if the mutation and the changed element are affecting hash. The reason is that the features from argument don't have any details about the relevant ancestor condition. Similar to the invalidation set approach, we can build a kind of upward traversal set with the features from argument and the features from the compound selector containing hash. Then this can provide a relationship between the mutation and the ancestors. If we have a mutation on an element and both the mutation and the element are affecting a hash state, we can have features for the ancestor of the changed element. When we meet an ancestor affected by hash, we can figure out whether the ancestor is relevant to the mutation or not by matching the ancestor with the features. So if it matches, we can invalidate it. And otherwise, we don't need to invalidate it because the ancestor is not related to the mutation. With this approach, we can add additional filtering condition for the ancestors. So these are about the simple case of class A has class B, and we have many other variations. We can use complex selectors as the hash argument, and we can use a hash selector as a subtree condition of the subject element. With some logical combinations, we can combine multiple selectors using hash, or we can use many pseudos in hash argument. Those have different problems, and those problems need to be handled by different solutions. So we will go through the other variations step by step as we've been doing. Okay, this is what I prepared for this talk. A lot of people are helping me during the this prototyping. Thanks to my Igalia colleagues and especially Brian for all the discussions, suggestions, and communication help. And thanks to Google Chrome team and especially Rune for the great reviews and guides. Actually, I'm learning a lot from him. And as always, thanks to IO for supporting this project. And thank you for listening. Okay. Thank you for listening. And I think we can have some Q&A time. So do you have any questions?
I have a live question, if you don't mind. So
Yep.
you said that thank you so much for presenting this, by the way, and working on this feature. I really appreciate it. You said that the running time could be in worst case n squared for computing the updates because a has can depend on any of its subtree. But your implementation optimizes that to be a single tree walk for everything together. Is that right?
Yes, right. So I explained that the repetitive argument matching was removed by some applying some has matching result cache. So currently we applied those solutions to remove those ON square overhead. So we don't have any problem now.
I see. And does it do one tree walk or two?
It's one tree walk.
For all style recalc.
Yeah.
I see. I see. So, and what about? I see. Okay.
Yep.
Interesting.
So you mean for all style walk? So I answered that we will need one tree walk for the argument selector. So for the entire tree walk, we need one more tree walk for argument selector, and as always, we need one tree walk for the style recalculation. So in this perspective, we need two tree walk.
Okay, so the first tree walk is to compute which elements match which the internals of the has function.
Yeah, right.
And then later you do the tree walk for all the elements. In order to recalc the style.
Yeah.
Do you think it's possible to get rid of the extra tree walk?
Actually, I don't think it is possible because we need to check the argument selector. So maybe maybe we can apply some approach of skipping those argument matching operations if we have any matching result from the previous recalculation. So, for example, we can keep some has matching status, and we can reuse those status in the next recalculation process if the has matching status is not changed. And so to apply that approach, we need to apply style invalidation first, because we need to update the stored matching status if the has matching status is changed. So we need to do the style invalidation first before applying that, I think. Yeah.
I see. Okay, thank you.
Thank you. So, okay, I think the time is up now. So thank you for listening, and thanks for the interest. Okay, then please contact me any doubt or question via mail or some other channels. Okay, thank you. See you.